Hello everyone, today I will present our senior design project called Solid State Transformers. This project focused on designing a compact and efficient 1 kilowatt power conversion system controlled by a microcontroller. Our project was developed as a team. Different parts of the project, such as control algorithm, circuit simulation, PCB design, were shared among team members. Ceyda Çoğal is a team leader, Turgut Mertaksu is a system design engineer, and Enver also is a hardware development engineer. And also, our advisor is Professor Dr. Hıdır Düzkaya. Uh, the main problem is traditional transformers have several limitations. They are bulky and heavy because they operate at low frequency. They also provide limited control capability and poor integration with renewable energy systems. In addition to this, they do not support intelligent monitoring or real-time control features. And our system was designed according to specific technical targets. The output power target is 1 kilowatt. The system provides selectable 24 and 48 volt outputs in both AC and DC forms. We also target efficiency above 90%, power factor above 0.99, and THD lower than 5%. And this slide shows the proposed system architecture. Our design uses a two-stage conversion structure. In the first stage, the AC to DC PFC rectifier converts the grid voltage into DC voltage. In the second stage, the isolated DC to DC converter and high-frequency transformer provide voltage conversion and isolation. The whole system is controlled by a microcontroller using PWM signals. This slide shows the detailed block diagram of the system. First, the MI filter suppresses electrical noise from the input. Then the AC to DC inverter creates the DC link voltage. After that, the phase-shifted full bridge inverter generates high-frequency AC voltage. Finally, the transformer and rectifier stages generate stable AC and DC outputs.
Hello everyone, my name is Turgut Mertaksoy and I will talk about design and implementation. Here we see the overview of system modules, and in this table the first column is modules, second one is inputs, outputs, and here's the last one is functionality of modules. The first stage is AC/DC stage, and here we see the filtering and rectification parts. EMI filter is suppressing the electromagnetic interference on the power line. These two thermistors are limiting the inrush current to protect the components. Full bridge rectifier here rectifies the AC. Here we have boost PFC circuit parts. We have inductor, MOSFET, diode, and capacitor. This circuit does the power correction, and here on this DC link we have nearly 360 volts DC output. Second stage is DC-DC stage. At first we have phase shifted full bridge inverter. Here we use it for MOSFETs, and here we are inverting the DC to AC with 50 kHz switching. After this part we have one high frequency transformer here, and this transformer steps down the AC voltage. Here we have full bridge rectifier again, and then with this LC filter we have pure DC at the output on this load. The control loop architecture. We have outer voltage loop and input current loop here, and we are producing the PWM signals and sending it to MOSFET. PCB schematic design. We see AC/DC schematic here and the gate driver of these MOSFET, and here we see the DC-DC schematic, and here these two circuits are the gate drivers of these MOSFETs. This picture is the PCB layout, and this one is the 3D body picture. And here we have the prototype of our product. We can see the start button here, fuses, EMI filter, and our circuits, and here we have STM microcontroller, and lastly we have a screen for information here. Testing and verification. These waveforms are the outputs of PFC stage. We nearly have 360 volts. This is the waveforms of the output of 48 volt situation, and we see that the ripple is almost 2.1%, and this one is the waveform of 24 volt output.
Hi everyone, I'm Emre Ulusoy. I'm going to start with input stage performance. One of the most critical metrics for the grid-connected power supply is total harmonic distortion. Our system achieves a current THD of just 3.68%, calculated over the first 50 harmonics. To summarize the AC/DC power factor stage performance, our input current THD of 3.68%, the power factor stands at 0.995, extremely close to unity, and the power factor stage efficiency comes in at 94.7%. For the isolated DC-DC stage, the calculated output voltage is 48.2 volts with a voltage ripple of only 2.1%. The total system efficiency from the grid to low voltage DC is 93.94%. This slide brings everything together in our design verification matrix across all 5K parameters. With the technical verification complete, let's shift our focus to the commercial side of the project. Breaking down the total components cost by subsystem, we can see the PCB, enclosure and miscellaneous items make up the largest share at 32%. The total prototype cost reached $4,035. This slide provides a detailed bill of materials breakdown. In terms of commercialization, we see three strong application areas for this design. Our design has been engineered with compliance in mind from the start. Let's touch on the engineering safety features. Built into the system, thermal control is handled through the intelligent fan activation, triggered for sensor mounts on the switching components. For surge protection, NTC thermistors ranging from 1 ohms down to 0.1 ohm, limiting inrush current at startup protection both the converter and the grid connection. And the entire system is housed in a 3D printed isolated enclosure.
Now I will talk about the sustainability and interdisciplinary aspect of our project. Our project combines different engineering fields. Our project supports several UN's sustainable development goals. SDG 7 supports clean and efficient energy. SDG 9 supports innovation and modern infrastructure. SDG 11 supports smaller and more efficient systems for cities. SDG 12 helps reduces electronic waste. SDG 13 supports climate action by reducing energy losses. Thank you for listening our project.